Hey guys, welcome back. Today we're going to be talking about temperature, heat, and basically heat expansion, and by comparison or by in contrast, cooling contraction. We haven't really described what heat is or what temperature is, and we've kind of avoided the subject up to this point. At this point, we kind of have to deal with this question because we're leading into some really important phenomena that are dependent upon our discussion of heat and temperature. So let's go ahead and start talking about it. The very first thing that we have here on our image is a nuclear bomb, right? Nothing explains, or nothing is hot like a nuclear bomb. The very middle of it can reach several million degrees. The outer part of it is about the same temperature as the sun. A nuclear bomb is a tremendous amount of heat and a massive temperature gradient. So, and this is what leads to a large amount of the damage ultimately. So anyways, here we see a nuclear test, this photograph here. This is actually a relatively small test, but it looks pretty ferocious. You wouldn't want to be in the middle of this. All right, so let's start talking about temperature and our background here, just as we're cruising through here. You'll notice that there's some dunes out here. So I actually, in our background, I figured for the temperature, you might as well go ahead and imply it by a picture of the Sahara Desert, which gets quite hot. So you'll see that in the background in today's lecture. All right, so what is temperature? Temperature is a number that corresponds to the warmth or coldness of an object. And it's usually measured by this thing called a thermometer, thermo, meaning heat, meter. It's a heat meter. It's a per particle property. We're going to talk about what that means. It means each atom in a material is contributing to that temperature. And we'll show you how here momentarily. There's no upper limit. There's no upper limit to how hot something can get. It can get billions, trillions, quadrillions of degrees. It can go to some infinite number of degrees, right? We don't know. But it does turn out that there is a definite lower end. There's a point at which you can get no colder. And that is something we'll describe here momentarily as absolute zero. So those of you that have ever lived in California or have ever traveled from Las Vegas to California have gone through the town of Baker. Baker is a great place to get Greek food and gaudy Denny's diner food. This good old days when fuel prices back in California, 155 used to be horrendously expensive. Now I wish I had that price. But anyways, here in the background, I'm digressing. Here in the background, besides the fact that we're in the Mojave Desert, which is also a hot area, is the world's largest thermometer. And you cannot go past this place without going past the world's largest thermometer. So I thought that was an apt way to start our discussion. So we talked about each particle having an effect. So temperature is proportional to the average translational kinetic energy. Remember, kinetic energy is the energy of motion per particle in a substance. So we have an animation of this over here. These are vibrating particles. This is actually kind of what atoms do. They sit there and they vibrate, or as in this case, molecules do. They sit and vibrate in substances. So the way that these things move inside of different substances and vibrate is dependent upon their state, right? In a gas, basically it's the vibration or how fast the gas particles are bouncing to and fro. So at a high temperature, they're going to be moving around like bullets. At a lower temperature, they're going to be moseying around fairly slowly. In a liquid, that's basically going to be how they jiggle and slide right around each other and past one another. And then, of course, a solid would be how fast particles move as they jiggle and vibrate in place. They're not going to be moving. So these are actually vibrating and jiggling in place. So this is much more like a solid. All right, so a thermometer measures temperature by expansion or contraction of a liquid, mercury or colored alcohol. Usually we use colored alcohol. Mercury is the old school way of doing it. The problem is that mercury is an environmental hazard and it can cause certain toxicity issues in people, especially it's a problem for pregnant women trying to have children. It can cause birth defects. So we usually use colored alcohol. Reading occurs when the thermometer and the object reach thermal equilibrium, which is to say having the same average kinetic energy per particle. That means that the temperature of the thermostat or the thermometer is the same temperature as the environment which it's measuring. You can't just stick it in and get an instant measurement. It takes a while. They have to come to the same level, and then you can read it. And of course, one of the better ways of doing it now, where you don't even have to touch the object, is in something called an infrared thermometer. And basically, you're scanning it for infrared radiation. And in doing so, you're able to get the temperature. So let's talk about what temperature is, right? We've been talking about this idea of a thermometer. We need to know what this means. Okay, so turns out there's more than one way to define temperature. The most common way in the world is the Celsius scale, which is named after a guy named Anders Celsius. Anders Celsius, he didn't live very long. You can see he lived from 1701 to 1744, about 43 years. And essentially, Mr. Celsius basically said that I'm going to set some degree, I'm going to just say the point at which water freezes, I'm going to call that 0, and the point at which water boils, I'm going to call that 100. And so it's going to be a straight scale between the two, from the boiling point of water to the freezing point of water. And everything's going to be based upon water. And of course, one of the things we need to keep in mind is that the boiling point and the freezing point of water are actually pressure dependent. Unfortunately, in our last lecture, we talked about Boyle's law. We didn't take the next step and go into the ideal gas law, which kind of implies this point. But with that said, we kind of have an understanding here. Fahrenheit, the Fahrenheit scale, which is what is used in the United States, most of the world uses the Celsius scale. But the Fahrenheit scale is named after a guy named Daniel Fahrenheit. I don't know what the G stands for. And he lived a little bit longer. These guys actually lived at the same time. And Mr. Fahrenheit here found that 32 degrees was the freezing point of water and 212 was the boiling point of water. And you might be asking, so why 32 and why 212? Well, you have to keep in mind that back in the time of Celsius and Fahrenheit, Mr. Fahrenheit needed to find a way to reproducibly calibrate thermometers over and over and over again. And what he did was he found that there was a certain salt solution that he can cool down repeatedly down to what he defined as 0 degrees. So it was a salt brine mixture, salt water mixture, that he can always cool down to this constant temperature. And he said, I know what that is, and I'm going to call that 0. And he could do that everywhere in the world. And so that became a very good point. And it turned out the freezing point of water on his system was 32 degrees. Of course, the next question is, why 212 for the boiling point? What was the other point that he was calibrating? So we had 0 degrees for the freezing point. What did he set for 100? Turned out 100 is the core body temperature of a human being. So he knew that there was plenty of human beings around. There was this brine that he could make reproducibly, and so as a consequence, he came up with a system from 30 that winds up being from 32 degrees freezing to 212 boiling. It was not based upon water boiling or whatever. That's just how it's kind of evolved over time. All right, so it doesn't mean that it was a bad system. It just means it's not a very useful system today. Today we should probably use the 0 to 100. It's a better system in some ways. Following on that is the Kelvin scale. And the Kelvin scale is probably the most superior of the three. Lord Kelvin, who was an absolute genius, he was well respected in his time. He was probably overshadowed by Einstein right as he died. And a lot of people didn't learn about Lord Kelvin. But if you had lived in the late 1800s into the early 1900s, you would have heard Lord Kelvin and of course Sir Isaac Newton, as the rock star scientists of the last 300 years. And now we don't speak of Lord Kelvin too much, even though he is absolutely one of the most important people of all science. And what he said was, okay, fine, 273 Kelvin, which is named after him, for the freezing point of water, to 373 Kelvin for the boiling point. Why? Because Kelvin realized that there was a point at which water or any substance could get no colder. And he said, we're going to call that absolute 0. 0 at absolute 0. And then he said, I'm just going to go ahead and use the Celsius scale in terms of the same size of the degrees, right? For each degrees, 1/100th of a degree gets you from 0 to 100 from boiling or from freezing to boiling. He said, I'm going to keep using that. I'm just going to go ahead and just translate that all over to an absolute 0 level. And so as a consequence, kelvins rather than degrees are used. So we never say 273 degrees Kelvin, even though even I fall into the trap of making that grammatical error all the time. We usually just say 273 kelvins. Okay. And this is by far the best way to go. Of course, really only scientists use that system. So heat, right? What is heat? Heat is internal energy transferred from one thing to another due to temperature difference. All right. So this is internal energy in transit. So those vibrating molecules are running into other molecules and making those vibrate, and it's that vibration then spreads throughout a system. That is heat. That's internal energy. It's a transference of energy. That is heat. Okay, and the flow of internal energy from a high temperature substance to a low temperature substance until thermal equilibrium is reached. We're going to be talking about this in another lecture as well. But it always goes from high temperature to low temperature. You wouldn't expect something that is of low temperature to start vibrating something of a high temperature and bringing it down, right? It's the other way around. The energy always flows from areas of high to areas of low energy. Okay, the internal energy never flows unassisted from a low temperature to a high temperature substance, which we just stated. This is usually measured in joules or calories. We've talked about joules or calories in a little earlier, but remember, joules are units of energy or also units of work as well. And the translation is 4.18 joules of heat are required to change the temperature of 1 gram of water by 1 Celsius degree. So that's to say 4.18 joules is equal to a calorie. All right, that's the definition of a calorie. So it's a quantity of heat, and the amount of energy or the quantity of heat is usually used in food analysis and dietary type stuff. So here we see a hamburger and cheese and all the other good stuff that you might like on your cheeseburger. Hopefully you like it. And there's a scale here to represent that they're measuring the amount of heat that's in it. So energy ratings for food and fuels are determined from energy released when they are burned. So to figure out how much energy is in here, they actually stick it in a furnace and they cook it. They actually burn it off to see what comes out of it. Units of energy, the calorie is common for foods. So heat unit for labeling food, a kilocalorie is 1,000 calories, and it's called a calorie with a capital C. So a kilocalorie is the same thing as a capital C calorie. And this is what you see in your food. The heat needed to change the temperature of 1 kilogram of water by 1 degree Celsius. So instead of a gram, which is a small calorie, it's a kilogram, and that is the large calorie here. So your hamburger here, let's say this thing's got 300 calories just in the hamburger alone. You're looking at the ability to heat up 300 kilograms of water by 1 degree Celsius, or 10 kilograms of water by 30 degrees Celsius. Right? That's a lot of energy. That's a lot of energy. Another feature of materials is something called see if I can get this out. Specific heat capacity. And it's defined as the quantity of heat required to change the temperature of a unit of mass of the substance by 1 degree Celsius. So we're talking about water, a calorie being required to improve or to increase the temperature of water by 1 degree. But it doesn't always take a calorie to increase everything. So certain things have lower amounts, and as a matter of fact, most things have much lower amounts than water. So it takes a lot less than 1 calorie to do it. And basically, it's a resistance to heating. So like thermal inertia, resistance of a substance to change in temperature. Whatever's hot tends to stay hot, and things that are cold tends to stay cold. It makes sense. There's not really a law for this. No, there's no momentum of heating or anything like this, even though certain physical attributes can be attributed to momentum. There's no law for it. But there's some consequences for this that are, in fact, laws. We'll come to those in future lectures. So specific heat capacity, so different substances have different thermal capacities for storing energy. For example, it takes about 2 minutes to raise the temperature of an iron pot of water to boiling temperature. So this is for iron. But it takes less than 1 minute to raise the temperature of the same quantity of water in a silver pot to boiling temperature. So that implies, of course, that there is a greater conductance of heat through silver than there is through iron. All right. This is one of the most famous people in American history, one of the most famous silversmiths that has ever lived in the United States. He's holding a silver pot. This is, of course, Paul Revere. If you're not familiar with him, you need to crack open a history book. And in fact, here is one of his famous silver teapots. A lot of people did not know that he was a silversmith, but he, in fact, was. And he was quite an eloquent silversmith, a very good one. And his pieces are sought after the world over. Not just because he was a patriot, but because he was a fantastic craftsman. So again, specific heat capacity, equal masses of different materials require different quantities of heat to change their temperatures by a specific number of degrees. So 1 gram of water requires 1 calorie of energy to raise the temperature 1 degree Celsius, but 1 gram of iron, so instead of water, let's change it to iron, it's 1/8 as much energy for the same temperature increase. So it's much easier to heat up iron than it is water. Therefore, water absorbs more heat than iron for the same change in temperature. So we would say in that case that water has a higher specific heat. As a matter of fact, water routinely has one of the highest specific heats of almost all materials. So here's a list of different materials that I found from the internet. This is in calories, per gram per degree Celsius. And water, of course, is defined at 1. But wood, for example, takes only 42% as much and it heats up pretty quick. Salt, 21%, 0.21. Gold starts heating up at 3%. So gold, it turns out, is a very good conductor of heat and electricity, probably the best on the periodic table to my memory. And it heats up very, very fast. So you get the idea. Alcohol is relatively low, but nothing comes close to water. Water has one of the highest specific heat capacities of anything that we deal with in nature. And of course, that has a major climate effect on the Earth, and it helps mediate the way that our climate works so that we don't have massive extremes like you see on planets without oceans. Okay, so we just described this. This is actually some discussion about the specific heat capacity of water, and that it's the higher capacity for storing energy than almost any other substance. Involves various ways that energy can be absorbed. So increases the jiggling motion of molecules, which raises the temperature. Increases the amount of internal vibration or rotation within the molecules, which becomes potential energy and doesn't raise the temperature. And water molecules can absorb energy without increasing translational kinetic energy. So it turns out that there's a series of different kinds of bonds that are involved in water molecules that allow heat to be transferred throughout the fluid in many different ways. It's not just one set of bonds that it's rotating against. It might be rotating against or vibrating against several different kinds of bonds. So it can translate and store that energy all over the place. All right, so it makes sense that the greater amount of jiggling in a solid, for example, the more space is going to be required. So if you heat something up, you have two atoms that are vibrating, next to each other translationally. As they're vibrating, they take up more space. And that causes things to expand. Most material substances tends to expand when they get heated up. So due to rise in temperature of a substance, molecules jiggle faster and move further apart. So one of the places where we see this are railroad tracks. Late on winter days, expand can buckle in the hot summer. And so here we see exactly this. This is rail buckling all the way up and down here. This is a real problem. This rail here is all expanded out, and this will have to be fixed. Otherwise, you're going to have a derailment. Imagine if this beam over here didn't move with this one. Fortunately, I can't remember what those boards are called now off the top of my head, but the cross boards here are connecting the rails across to prevent them from separating one from another. And of course, you can also warm up a metal lid on a glass jar under warm water, and that helps loosen the jar because the warm water expands the lid greater than it expands the glass. All right, so there's a differential in how these things behave, and you can take advantage of that to help open up lids. All right, so knowing that things expand, we have to take that into consideration when we're doing our engineering. So in this case, we see, using reinforced steel with the same rate of expansion as concrete. So we would create expansion joints on bridges. So this is an expansion joint here. These are sawtooth. And as the bridge contracts in the cool part of the day, these things pull apart, and these teeth help keep the bridge intact so that it can be used during the daytime. And then, during the evening when it's cool. During the daytime, in reverse, the bridge tends to heat up, cars start going over it, and that causes heat. And what happens is the bridge actually starts to expand, and these teeth close this thing up. So this is a thermal expansion joint. The same thing happens, this is concrete. you'll find that when you lay concrete, it's best to go ahead and to put thin zones of cracks in here, because thermal expansion is going to set in. Your concrete's going to get shrink in the evening and expand in the day. And it's best to go ahead and put places where that breakage can occur most favorably. Otherwise, it's going to break right across your pristine concrete, and it's not going to look very attractive. So you'll see people lay these lines in here. Most masons will do this, or concrete layers will put that in for you. So we could take advantage of this for a couple of different things. You know, you can have two substances that expand at different rates. So say at room temperature, you can take these two pieces of metal, brass and iron, and it turns out brass has a greater expansivity than the iron does. And so if you put ice on the brass is going to contract more than the iron will, and so the whole thing will arch up this way. And of course, conversely, if you put we're just assuming the ice goes all the way through it, but it's still going to arch up. It doesn't matter if you put the ice on the bottom. If you put the iron and the brass above a candle, and there's heat that's coming into contact with it, and there's heat flow actually coming up into the system, the brass, again, is going to expand in this case. It's going to push out, more so than the iron, and it's going to arch down like this. And these are called bimetallic strips. You can read about this. I have a little thing here. But this is oftentimes used for regulation valves, for temperature gauges or thermostats and all kinds of different things. If it gets too hot or too cold, it'll bend one way and it'll turn on or off a circuit, whatever. And this has been used as a standard technology since before World War II, back into the 1920s even. So yeah, used in heaters, ovens, oven thermometers, refrigerators, and electric toasters. As a matter of fact, oven thermometers, you see these all the time used. All right, so we need to also talk about the fact that not all the time do we see expansion operating the way that we expect it to. Again, we got to deal with ice. We got to deal with water. Ice and water behave so differently than everything else we've talked about in this class. Especially the last several lectures, that we kind of need to take several slides and really lock in what ice and water do. Okay, so in most cases, say iron, you take iron and you melt it, the molten iron is less dense than its solid form, its pre-molten form. And so the consequence of that is that if you were to take a piece of iron and you dropped it into its liquid form, the molten or the solid form would drop right down through it down to the bottom. In water, the exact opposite happens. The solid form floats up on top. And this is abnormal for almost all substances that we know. All right, so why does this happen? Well, when water becomes ice, it expands. Ice has open structured crystals resulting from strong bonds at right angles that increase its volume. This makes ice less dense than water. So this is what ice looks like. Nice hexagonal bands in all these different directions. But when it's liquid water, it's actually more dense. These molecules, all these bonds are broken. They're moving around more. There's sliding and slipping going on right here. But that's not the case here. And so that makes ice less dense. It's more expansive. And as a consequence, it tends to float. All right, so now we kind of got to deal with the thermal expansion of water. Water, for a while, will act like other substances and change its density in accordance with it, but not when it's between 0 and 4 degrees. So let's talk about it as we change water's temperature from 0 on up above. So as temperature of water at 0 degrees increases, more of the remaining ice crystals collapse. So back here, at about 0 degrees, this ice starts to break up into this stuff here. Okay, so we get a sudden increase in the density. It starts to increase. And that's what's being shown up here in this graph. We have ice. This is the density of ice. And then all of a sudden, it breaks off down to here into liquid water. Now, let's look at this little zone right here from 0 to 18 degrees Celsius. This goes all the way up to 100. We're not going to worry about that. Let's just look at this zone in here. You'll notice it's a nice curve. So the melting of these ice crystals further decrease the volume of water, or volume of the water. Two opposite processes occur at the same time. Contraction and expansion. Both are happening at the same time. right? The contraction is occurring as a consequence of the phase transition from solid to liquid, but of course it's warming up, so the liquid is actually expanding, and so they're competing one with another. The volume decreases as ice crystals collapse, while volume increases due to the greater molecular motion. Just stated that. The collapse effect dominates. So noticing this, the collapsing effect dominates until the temperature reaches 4 degrees. After that, expansion overrides contraction because most of the ice crystals have melted. So you actually do have residual crystals in some form. They're not very good forms from 0 to 4 degrees Celsius. It's still water, but you still have somewhat of a slushy kind of bond structure that's working in that water that tends to give it this curve, this density curve with respect to temperature. So you actually go from its most dense point is at 4 degrees Celsius, right here. So it's actually at this density twice, here and again at about 9 degrees Celsius here. And then only once it gets above 9 degrees does its density begin to go the opposite direction, back up that curve. All right? Water is the only thing that is kind of abundant that you need to be aware of. It's kind of the exception to the rule. Unfortunately for us, it's a huge exception because it dominates 70% of the surface of the Earth. So we have to discuss it. All right, so let's go ahead and reiterate this. When ice freezes to become solid ice, its volume increases tremendously. So this is going the opposite direction. As solid ice cools further, it contracts. Density of ice at any temperature is much lower than the density of water, which is why ice floats on water. And so here we see this exhibited perfectly. Here we see a bunch of ice cubes, both in a glass and in a pitcher. And we'll notice that most of the ice, it's all floated up here at the top. None of it sitting at the bottom. It's floating up here at the top. And most of it is underneath the earth, or the water surface, not the earth's surface, but the water surface. But there is, in fact, some ice sticking up above this. All right. This is analogous to the way that an iceberg floats. This is a photograph of an iceberg. You'll notice that most of the iceberg is well underneath. It almost looks like a tooth floating in the water. Most of the iceberg is below the water line, but there is a tip that sticks up out here on top. And so most of it is, about 9% of it, I think, is the number, actually, of the mass is actually up above the water. And the rest, 91% of it, is below. All right? So I guess that's kind of what we had to say about water. And that concludes our discussion on heat and expansion of actually thermal kinetics. If you have any questions about this stuff, I think it's neat stuff. We're kind of leading into some laws of thermodynamics, which is how the transfer of energy causes things to actually happen, such as the changing of phases of state or states of matter. So anyways, don't want to get too far ahead of myself. We'll let those lectures come when they come. If you have any questions or want to contribute to the discussion, feel free to meet me on the discussion board or send me a private email. Until next time, have a good one.